So if we were doing this in class, I would be asking you to graph both of these. I suggested putting it in slope-intercept form, although you could graph them with X and Y intercepts. So graph each equation on the same set of axes, and then I want you to come up with where do you think the two graphs intersect. So go ahead, pause the video, and try and do that. So I'm going to go ahead and solve these both for y, putting them in slope-intercept form. So for this first one, I'm going to subtract 2x from both sides. I get negative y equals negative 2x plus 11. And that means y equals 2x minus 11. So when I graph this, I'm going to go ahead and do my vertical scales by 2's. And I'm going to do my horizontal by 1's. So negative 11 is my y-intercept, and my slope is positive 2, so if I go up 2, and remember that means I'm up to this spot, and over 1, so you have to pay attention to the scale, just don't count boxes. So up 2 puts me here, and over 1, and I'll do a few of those. So here's my graph. So I'm going to graph this line. And then I'm going to graph the other one. So I think I'll do this one in green. So we get y equals negative 2x minus 1. So my y-intercept is negative 1. My slope is negative 2, so down 2 to the right 1. And I get my graph. So if I graph this, and then my question was to find where they intersect. So it appears, when I look at this, it appears that it intersects at the point 2.5, negative 6, as far as I can tell if I've done a careful graph. So sometimes it's hard to tell exactly where it intersects. And one of the things that we're going to be doing in this chapter, in chapter 3, is looking at something called systems of linear equations. And that's exactly what we're doing right here, is we're looking at a system of 2 linear equations. Sometimes you can have more, sometimes you can have 3 equations or 4 equations. So we're looking at this system of linear equations, and we are looking for the solution to the system. And the solution to the system is where the graphs intersect. And in this case, they're going to be lines. Okay, so again, this chapter, this section, we're looking at systems of linear equations. So on your worksheet that you did for homework, let's go through these graphs. So we have y equals 1/2 x plus 3. So you should plot the y-intercept. We're going to go up 1 and over 2. Hopefully you guys are getting to be experts at graphing linear functions. And so we can graph this. And y equals 4x minus 4. So my y-intercept is negative 4. My slope is positive 4. Up 4 and over 1. So we can graph this. And notice this time, it's really easy to tell. One of the things you were asked to do was find where the two lines seem to intersect. And here we can tell for sure they intersect at the point 2, 4. So what that means is that 2, 4 is the solution to the system of equations. And you should be taking notes on your homework paper. So that means that the x and y value, if I plug in a 2 for x and a y for 4 into both equations, the equations will be true. Both equations will be true. So when our two intersecting lines have one unique solution, we call this system consistent and independent. It's consistent because it has a solution. Some systems of equations the lines won't cross, and we would call that inconsistent. So this is consistent because the lines do cross, and it's independent because there's a unique solution. So we have consistent and independent are the words that we would use to describe this system of linear equations. For this next one, we have y equals 4. So that's going to be a horizontal line. And then y equals 3/2 x plus 1. So we're going to go up 3 over 1. Oh, I'm sorry, up 3 over 2. Or you can go down 3 and to the left 2. And we can tell again, right here, we see that they cross at the point 4, 2. Again, that means that 4, I'm sorry. Yeah, I just did say that, and I don't want to start over again. I thought, no, that doesn't look right. 2, 4. Okay, so the point 2, 4 is where these two lines intersect. So using these two values, if you plug them in for x and y, notice one equation, there's only a y, you get true statements for both of them. So this is the solution. So again, this has one unique solution. So we would say our system is consistent and independent. Now, this is a system of linear equations. You can also have systems of nonlinear equations. We'll see some of those later, but right now we're just focusing on linear equations, most specifically just a system of two linear equations. Again, the point 2, 4 would be considered the solution to the system of equations. So next we have y equals 2/3 x plus 3. So again, I'm going to scale by ones. So I have up 2 over 3, or you could go down 2 to the left 3, and we'll connect that. And then we have negative 2x minus 4. Because I know I'm looking for where they intersect, so I'm going to go up 2, which is positive, and to the left 1, which is a negative. You just have to make sure one of your directions is negative. So up 2 to the left 1, and we're going to connect this. And we're looking for where the two lines cross. Oh, can't really tell on this one, can we? So it's kind of hard to tell on this. So we're just going to kind of give it an estimate, which I think is what I said to do on the directions. So this one is about negative 2.5 maybe. And my y looks like maybe 1.5. Okay, so if I wanted to think about, well, how do I know if that's true? How do I know if that really was the solution where they cross? Well, what I can do is I can plug this in. This is my x value. This is my y value. So if I substitute negative 2.5 in for x, I should get 1.5 for y for both equations. So we can check that out. So you can see I plugged that in. And that doesn't appear to be it because I got a 1 and I should have got a 1.5. It's not going to work in the other equation either. So that's not it. Now we're just looking for about what is it. But this is a clear example of why solving a system of equations with graphs is not always the best bet, because a lot of times you can't tell exactly where the two lines are crossing. It was easy when they were crossing on a grid point that we could actually see exactly where they were crossing when we were plotting our slopes. But this one, not so clear. So we're going to have some algebraic methods to find the system of equations, and now here's a perfect example of why that's important. All right, so let's try this one. We've got a positive 1. Oh, lost my pen tool here. And negative 2/3 is the slope. So we'll graph that. All right, and then we have two, on this one, I'm gonna go ahead and use the X and Y intercept method. So if I let Y equals 0, I get X equals, remember the little cover up, this would be gone if Y is 0, so I get X is 4.5. So I'm gonna plot that. And if I let X equals 0, I get Y is 3, so I'm gonna plot that. And I'm going to graph my line. And this would extend. I'm just going to draw arrows there, but it would extend. Notice here that the lines don't cross. We have parallel lines. Now, I would have noticed this. If I would have solved this for y, I would have had the slope was negative 2/3, and you would see that you had the same slope. Remember, parallel lines have the same slope. So these don't cross, which tells me there is no solution. Remember, the solution is where the two lines would intersect. So there's no solution. And we call this system inconsistent. We don't say dependent or independent because it's just inconsistent. So no solution means that it is an inconsistent system. And that also tells you that the lines would be parallel. And then the last one we did, we have the line y equals negative 1/2 x plus 3. So I'm going to plot that. And on this one, I'll go ahead and use the X and Y intercepts. The x-intercept, if y is 0, x would be 6, which is right here. And if x is 0, y would be 3, which is right here. Well, that's interesting. Because notice when I connect these, I'm going to kind of draw it so that you can see both colors. But notice here that it's the same line. Now, I would have noticed this if I would have changed this so it was in the same format. I had one in slope-intercept form and one in standard form, so you don't always recognize that those really are the same line. But they are. So they're the same line, which means every place on the line is a solution. So there are infinite solutions. Every point on the line is a solution, and we say that this is consistent because there is a solution, and dependent. So these are the words we would use to describe a system of equations where you have the same line. Now, I do want to point out that this is not the same. Infinite solutions is not the same as all real numbers. You can't say the solution is all real numbers. It's infinite solutions because there's infinite points on the line. But they're only the points on the line that are solutions. See all these other points out here? Everywhere that's not on the line, which there's also infinite non-solutions. So you can't say all real numbers when they're the same line. You can say infinite solutions, but you can't say all real numbers, and hopefully you understand the difference on that. So this is called consistent and dependent. So that's how you do systems of equations, linear equations, and the words that you use to describe them and the different situations that you could have. So wanted to make sure you had an understanding of that.